Okay, perfect. Okay, so welcome everybody to our distinguished seminar for this week. I have the great pleasure of introducing Professor Garud Iyengar from Columbia. So Professor Iyengar is a professor in industrial engineering and operations research in the School of Engineering and Applied Science at Columbia University. He received his BTech in electrical engineering from IIT Kanpur and his MS and PhD in electrical engineering from Stanford. His research interests are broadly in control and optimization, and his published works really span a diverse range of fields, including information theory, applied math, operations research, economics, and financial engineering. And his current projects are equally diverse in the areas of large-scale power systems, to reinforcement learning, to modeling of cellular processes. And so today, Professor Iyengar is going to give a talk about Shapley meets uniform and axiomatic framework for attribution in online advertising. So I'll let you take it away. Thank you again for agreeing to come.
Thank you, Tim. Thanks for the invitation. It would have been wonderful if I could join in person, but virtual is great. I'm going to be talking about work that is joint with Raghav Singhal, who is an alum of this department. He's now a faculty member at the business school at Dartmouth. And pretty much by way of background, the other four authors and myself, or that is the four authors, we struggled at this work for about 2 years before Raghav joined the project, and he quickly brought it to the shape that it's in right now. So I'm happy to present it, and I'm happy to present some work that was generated by people who graduated from this department. All right. Where you go. So motivation. Digital ad spending has been increasing worldwide. So this graph was taken from a source before COVID hit. So I don't know how these graphs have changed, but my suspicion is that the total ad spend on digital media has actually gone up over the time than down. And as a result, the volume of these ads is so big that these ads cannot be bought on an individual basis or through using techniques that, say, TV ads were bought. There is algorithmic buying of ads going on. The bids and automated actions are put on multiple channels. One has to develop an algorithm for putting these ads, and those algorithms have to particularly price or value the ads. So the key in the decision-making of these digital ads is what the value of an ad. And the central question in the industry is, how can the advertiser attribute a value to a targeted ad? Now, the story of attribution has been around for as long as ads have been around. I won't go into the details of all of this, just to give you a feel. The father of modern advertising didn't quite know which half of his advertising money was working. There is claims that the new .com bubble is online advertising. This is a report from November 2019. There was a paper that appeared in 2015 which said, what did the ad stop at eBay accomplish? Absolutely nothing. Facebook ads are far less effective than we thought. This happened in 2019. Not sure what implication that has for politics, but in any case, in the ad space, it isn't clear what works, what doesn't work, how to value ad, what happens. So we have big data, as in we have lots and lots of data about ads being placed digitally. We have lots and lots of data about how customers are interacting with these ads, but that hasn't quite translated into a systematic framework for assessing the value of an ad. Attribution, or this ad attribution, has been repeatedly classified as a tier 1 research priority by the Marketing Science Institute. It was in 2016, it was in 2018, and I would imagine that this will continue to be the case going forward. So the main question that we try to tackle in the paper and this talk is, can we develop a systematic framework to understand the value of a targeted ad? So there's this word targeted ad, and I would like to spend some time trying to explain to you what a targeted ad is. Before we get there, I'll tell you some heuristics that are currently in place. So the mental model that you should have in mind is that there's a single user. He or she interacts with a sequence of ad actions. This could be emails, this could be banner ads on a website, this could be a text message, this could be a search ad. And all of these things, all of these interactions actually get them through a process starting from when she is unaware about a product to a point where she desires the product and buys it. And the question, the name of the game here right now in attribution is, what was the value of each of the ad actions that she saw on the way to this final conclusion, which is converting or buying the product? One of the heuristics that's used is called last touch attribution. So the last ad gets all the value. Typically in the digital domain, what's happening is that you might end up seeing an ad, you might get an email, a Facebook ad. Ultimately, you might actually go to a search engine, generically Google here, search for the product and buy it. But because you came from the search engine to the completion state, to the buying state, typically, not typically, but in the last touch attribution, all the value gets attributed to this last touch, which is search. If you think about it for a moment, there's a big incentive issue. If all the value gets attributed to search, Facebook may not be as inclined to show your ads because it doesn't get as much value out of those ads. There's another possibility of uniform attribution. This is also simple and somewhat fair. So everybody, all three ads get equal value in this case. Another one that had started to get some traction was something called an incremental value heuristic. Here it has some counterfactual reasoning. And the way to think about this is that let's say that we sent first an email, or in this particular example, we are talking about a Facebook ad. So the value that will be assigned to the Facebook ad is the change in the conversion probability if the ad was not shown. So we have to look at the actually observed action, which is that ad was shown, and a counterfactual action, which is the ad was not shown. And the difference between these two actions is what would be attributed as the value to this ad. And so it has some notion of counterfactual reasoning. But on the face of it, all of these seem rather ad hoc. And there isn't a fundamental way of thinking about these problems. So one main motivation for this work is how do we get an axiomatic framework for understanding what is a fair way of allocating value to all the various ad actions that took place along the way. This particular problem has been seen in various different literatures, in marketing, in operations, in causality, in economics. And for interest of time, I will not go into the details. If you have any questions, I'm happy to discuss it offline or during the question and answer session. Just wanted to flash this to show that this is an important problem in many different fields. So let me start with what we call a targeted ad. And this will give you a motivation for the model that we'll be using later on. Sure. So here's an example. We have, let's say, a customer who starts off in an unaware state. You send them an email. As a result of that email, in this particular state, you take the action of sending an email. You could, if this person interacts with the email, it gets to an aware state. If there is no interaction with the email, they go into an unaware state or still remain in the unaware state. Now you have the possibility of measuring what the state of the customer is or the user is. And based on that, you could take a different action. You could show them a Facebook ad if they are aware. Otherwise, you take a no ad action, meaning you don't take any action. If they interacted with the Facebook ad, perhaps you go and buy a search ad. And as a result, in the interested state, you get them to interact with the search ad and convert. In the other two states, because you measure what the state of the customer is, you don't take any action. So a targeted ad consists of two things, the user state and an ad action. Together is what we'll go to call a targeted ad. Here's a running example that we'll be looking through to show various different strategies and what happens. So this observed user path or something called conversion funnel in the marketing literature. You start from unaware, somebody shows you an email, you became aware, We show you a Facebook ad, you become interested, you go to the search engine, and then you purchase the product. And the name of the game is which of these three actions, ad actions, deserved how much of the final conversion that you ended up getting. So the targeted ads drive customers on a network. Nodes are the states, edges are the transitions. The question we are after is how much value to assign to each of these targeted ads. And the challenges here are the cooperative effect, meaning that all three ads together land me into conversion. And so there's a cooperation that is going on between the ads. And the other story is counterfactual value. What if I didn't show that ad or didn't take that action? Could people just on their own organically have taken the action that they took? As a result, that ad should not have gotten a value. So cooperation and counterfactual are the two things that are going to be important. And for those of you who have seen cooperative game theory, you should immediately start thinking about one of the solution concepts there is Shapley value. And therefore the title goes Shapley meets uniform. So the Shapley part is coming from looking at cooperative effect. And later on in the talk, we'll show you how to take the counterfactual effect and put it into Shapley value so that you get a final answer. Problem motivation is done. We're going to talk about some shortcomings of the existing heuristics. I'll build an axiomatic framework for you. I'll show you how that axiomatic framework in a Markovian model will work well. I'll talk about some data, and then I'll stop and take some questions. So remember, this was the generic example that we were looking at. It goes through an email, a Facebook ad, a search ad, and then completion. In the last touch, the last targeted ad gets all the value. So if you look at the three actions, the first two actions get 0%, and the last action gets 100%. In the uniform attribution, all three of them get uniform value, so get a third each. These are both budget aware. This is a concept that's going to be useful later on. We will have whatever we earn is what we want to attribute. We don't want to attribute anything more. We might decide not to attribute anything or some part of it if we decide that that was not generated by the ads, but we certainly don't want to go more than what we earn. IVH, this attributes the lift with respect to no ad. So in order to understand the lift, we have to understand what would have happened if we had not shown the ad. So let's assume that if we didn't show the ad, then the customer is just going to quit. So in the state 1 and 2, if you don't show the ad, the customer is going to quit. So the entire contribution of the forward-going chain must come to the ad in those two states. In state number 3, whether you show the search ad or not, they've already reached this particular state where they are going to purchase. So there, whether you show the ad or you don't show the ad, you'll end up getting the same action. As a result, that particular ad should not get any attribution. So if you do the IVH, which is called incremental value heuristic, the third ad will get 0%. So it's counterfactual. It does take into consideration the fact that if your action didn't matter, you should not get an attribution. But what happens to the first two? It turns out both the first ad and the second ad will end up getting 100% of the value. As a result, the incremental value heuristic, which we'll define in a formal term soon, is not budget aware. It's giving away 200% of what it earned. That's certainly not going to be feasible. But the first two are not counterfactual. They don't take counterfactual into account. They're budget aware. And so what we are targeting is trying to get an understanding of what is a strategy that's relatively simple to operate, is budget aware, and it's counterfactual aware. And so we want to build a set of axioms that will make sure that the strategy is well-founded. So we develop a new attribution metric. We give an axiomatic justification. We show how to compute this metric in a common user behavior model, which is driven by a Markov chain model, and show how this Markov chain simplifies how this metric can be computed. And then I'll show you experiments on a large real-world data set and see what insights can we gather. So here's where things are going to get a little technical, so I'm trying to see how much of the idea I can get across. So here's the setting. We have a collection of targeted ads. And remember, what is a targeted ad? A targeted ad is a state and action pair. So all pairs of states and actions are going to be called targeted ads. Script X is going to be a subset of these targeted ads. So there'll be a subset of actions and states that are going to be taken that I'm going to collect as a collection. And then I'm going to say, what is the value of this subset? Where does this notion come from? This notion comes from coalitional value in cooperative games. Because I'm interested in counterfactual, I have to think about a counterfactual of a particular ad action P. So if you look at this particular state 1, the action there is to send an email. The counterfactual to email in state 1 is no ad at state 1. So I'm not going to show an ad here. I'm not going to show the email here, but everything else remains the same. And I want to understand what happens when I take the counterfactual action. Pi of P is the attribution that would be given to the targeted ad P. And I want to understand what is this value. This is the pi of P is what I'm after. And what I'm going to do is put a certain set of axioms to define how this pi of P should be computed. So the first axiom that we want is the following. We want to make sure that the total sum of all the contributions to all the players, so P or all the targeted ad action, if I sum up over all possible actions, that's going to be less than equal to whatever was the value that was generated by the entire system as a whole. This minus counterfactual value basically sets this up as an equality. If you look at an inequality, I want the contribution that will be given to each of the ad actions should be less than equal to the total value. And what happens to the remaining value? The remaining value is a counterfactual value. This is the organic value or the impact of offline efforts. When you look at data, I will show you that there are often situations where without taking any action on your users, a certain fraction of them convert, meaning you get them without any effort. As a result, the value generated by those customers should not be given to any of the actions. Null player. So if a particular action does not do anything, then it should not be given any attribution. So here's the operationalizing of that idea. Take any subset of state and action pairs, take any subset of targeted ads, which is what we call state and action pairs, remove the current state action pair or this current targeted ad that you're trying to look at. To any such subset, if you add that targeted ad, or you add its counterfactual, whether you send the email or you don't send the email, the final action is the same regardless of what you do downstream, or whether you show an ad, a Facebook ad or not. If you do everything else the same, the value is exactly the same, then that particular ad action should not have received any value. That seems fairly simple exercise. The next thing is we're going to impose something called symmetry, which what they're trying to get at is that equivalent targeted ad should receive the same attribution. Now, I've put the equivalent part in quotes because it's not clear how to define what equivalent means. In our setting, what we are going to define is that if you look at the counterfactual value of an action P, what is the counterfactual value? The first term here, X union P, tells me what is the value I generate if together with X, I add P. X union P counterfactual means what happens when to add X, I add the counterfactual value of P. The difference is the lift associated with taking the ad action P. If it so happens that the lift from P is the same as lift from R, and then the value that I get from adding P and the counterfactual of R and counterfactual of P and R are equal. If those two conditions hold, we will say that these ads are equivalent, and therefore the attribution that you end up getting will be the same. Finally is linearity. If I have completely two different value functions, then the attribution of the sum of those two value functions must equal the attribution that you get from each of them. So these are basically Shapley value axioms modified to account for counterfactual. Remember, in the beginning of this talk, or rather towards the beginning of this talk, I talked about the fact that there are two difficulties in this attribution literature. One is to understand cooperation, and the other is to understand counterfactual value. Cooperation, we are capturing from the Shapley value axioms, and we are modifying them to understand and to capture counterfactual behavior. What we are able to prove is that there exists a unique solution to the counterfactual axioms. To these axioms, there is a unique payment scheme. And the unique solution here is something called a counterfactual adjusted Shapley value. And the way it's computed is the following. For each targeted ad, you define this, look at all subsets of actions which does not contain this ad. For each of them, you define the value ad of P over its counterfactual. This is the lift if you were using just the actions in script X. How do you weight them? You multiply them with a certain probability. For those of you who know Shapley value, you can see that this probability is an ordering effect. You don't know in which order the elements in script X came. And if they came in any random order, then the probability that script X came before this player and then the rest of them came after this player gives you that quantity. It's not very relevant. The details can be worked out, but the important thing is that it's looking at the value ad and then it's averaging over all possible orderings. So it's the expected value ad over the counterfactual. And that is the unique solution to these axioms. And the proof idea is to basically use that it's a Shapley value is the unique solution to the non-counterfactual axioms. I want to stop here and just argue to why, just a second to tell you why am I worried about these axioms. So in many of these settings, one of the things that we are after is trying to understand what is the right attribution strategy. And one way to get to the right attribution strategy is to say, look, I'm going to set up a set of axioms and say that I believe that these axioms should be valid for any attribution strategy that one wanted to think about. And if you believe that these 4 axioms are something that you want in any attribution strategy, our first result tells you that the unique solution is this particular strategy. You can quibble about whether those axioms are right or wrong, but if you agree, then this is the only answer. And that gives some robustness to what we are after. But is this tractable? It turns out that it's not tractable because you have an exponential sum here over all possible subsets. And so in general, this is not going to be a very tractable strategy. Oops, what happened here? And so one needs to figure exactly how one is going to. In order to do that, what I'm going to do is switch to Markovian model and try to give you an understanding of how we can compute this counterfactual adjusted Shapley value in a Markovian setting. Tim, do we have any interesting questions that need to be answered right away, or can I continue on?
There are no questions right now. You're welcome to continue.
Okay, perfect. All right, great. So now what I'm going to do is switch gears a little bit and try to build a Markovian model. And the reason I want to build a Markovian model is to go back and answer the question of an efficient computability of the counterfactual adjusted Shapley value. So there's going to be a little bit change of pace here, and then we'll go back and connect it to counterfactual adjusted Shapley value. So here's the model. So at any given point in time, the user is going to be in some state S. This could, in the data that I'm going to present, this state is always observable, but there are extensions possible for a situation where there's some elements of the state might be latent. That's not something I'm going to discuss today. So let's for the moment assume that this is an observable state. In that particular state, different users come in with some rate lambda S. And in that particular state, I have a stochastic add action policy. What do I mean? I have a collection of ad actions. I could send them an email. I could show them a display ad. I could maybe send them different kinds of emails and so on. And I would do that with a fixed proportion. So beta AS tells you a fixed stochastic policy. This is the probability that I used action A when the user is in state S. After seeing the add action A at state S, the user transitions to another state S prime with some probability that depends on the current state S and also the action A that was taken in that state. And this process repeats itself until the user converts or quits. There are only two absorbing states in this Markov chain: converts, in which case I get a value of 1, and quit, in which case I get no value. So the add policy is a collection of these frequencies beta AS for all SA that belong to the state action pairs. A includes the no add action. So I'm explicitly allowing for the possibility that I decide not to do anything in a particular state. So the sum over A of beta SA is equal to 1, but one of the actions is the no add action. So now let's say that we have a set of targeted ads, script X. This is the collection whose value we need to define. If I have an efficient way of defining the value for this script X, I can go back and at least have a value sitting in the counterfactual adjusted Shapley value. I still have to worry about that infinite sum, but I'm hoping that that infinite sum in a Markov chain setting can be written as an expectation, and potentially I can compute that expectation efficiently. So I'm going to define V of X to be the probability of a random user making a purchase given that only the action in script X are available. So what does that mean? If a state action pair belongs to script X, it's a targeted ad that I am using, then the transition happens according to PASS prime. If, on the other hand, I'm not using that targeting action SA, that means SA is not in script X, then with probability 1, the customer quits. They come to that state, and they just quit. And this is how I'm going to define the value of a particular coalition of targeted ads. The next thing I have to define in order to do this counterfactual adjusted Shapley value is what does it mean to look at a counterfactual of a particular action. So let's say in state S, I show ad A with probability beta AS. Then the counterfactual player for this particular action would be that I will show the no ad with the same frequency beta AS. Whenever I was supposed to show ad P, take the ad action A in state S, I will end up showing you no ad at that time. So this is what I'm going to define as counterfactual. So the setting is, I've got a Markov chain. Depending on what actions I take in the Markov chain, customers move around in this Markov chain. I get value if they land up in the set C, and eventually they leave the system by either going to Q or C. When I'm looking at a subset, if I don't use any of those actions, the customer quits. The counterfactual value is defined as every time I wanted to use an action, I ended up using the no add action otherwise, meaning I did nothing. So what happens to the last touch? The last touch attribution can be written as an expectation over two things: an indicator function that a particular path P to the Markov chain. So P is a path drawn from the Markov chain. That path converts. And if it converts, the value along that path for a particular state P has been defined as simply P is the last ad in the path P. You take the expectation over all paths generated from the Markov chain. The attribution that you end up getting is exactly the last touch attribution. So in this particular example, you get, let's say we have a two-state example, the Facebook ad would get 100%. What happens to uniform attribution? Uniform attribution, the formula remains the same. You get a value only if you convert. But if you do convert, then every node along that path gets equal value. And by uniform, I'm counting the number of times the node appears. So if the node P appears NP times, I give it NP divided by the total number of nodes in that particular path. That's what uniform attribution ends up doing. And one of the problems with uniform attribution is the fact that if you have a node which cycles for a long time, then this node 1 which is actually a very ineffective node in actually pushing traffic forward, ends up getting higher valuation as P goes up. And the valuation, the attribution to node 2 becomes lower, which is something bad that we'll have to correct. Now let's look at what happens to incremental value heuristic. And for that, we'll have to bring in the counterfactual. So that's the Markov model. In the counterfactual Markov model, instead of using P, I'm going to use the no add with the same frequency. So P here, this blue thing refers to the action P, the orangish thing tells you no add. So instead of using P, I'm using the no add. And the incremental value heuristic can be approximately thought of as the difference between the probability of conversion under M and the probability of conversion under MP. And what do I mean by MP? That's the counterfactual model where for the player P, I've used a counterfactual action. So the difference between these two conversion rates is approximately the incremental value heuristic. And the reason I'm saying it's approximate is because it turns out that these heuristics, the way it's implemented, it's not exactly the way it's done here. But that's a detail that we'll worry about. So in terms of incremental value heuristic, it will give you 100% for both of them. And then it'll break the budget. So now, at least this Markov chain allows us to now have a way of looking at what happens to all of these attribution schemes within a particular model. And within that model, we're going to look at what happens to our attribution. So the CASV was defined as a weighted combination WX of the lift corresponding to each of these, adding P to any of the coalitions X. So it turns out that under the Markov model, the CASV turns out to have a very nice description. The first part of it is you take the Markov model as is, and you take a slightly different version of uniform. So you look at if P converts, then you give to every node P on the path 1 over the number of unique state add pairs in the path P. So you don't count a pair a second time if it comes multiple times, you just count it once. So you look at the number of unique state action pairs that are going to be in the path, and you give them equal contribution. What's the minus thing? You do the same thing, except that now the paths are coming according to the counterfactual Shapley value, counterfactual Markov network. So the difference between them, between these two quantities, turns out to be the CASV. It has a very simple, crisp characterization. And in the interest of time, I'll not go into the proof of this. If I have time or there are questions, I'll tell you how this proof is constructed. It's a very nice use of carrier games, and it has some interesting ideas on their own. So let's apply it. Remember this example of using uniform versus unique uniform? In the uniform, as P goes up, the contribution to 1, the total value that 1 receives keeps going up. But in the unique uniform, in every path, 1 appears and 2 appears. Both of them appear, so they get 50% of the thing. And if you look at this example, both these nodes are needed for completion, and their contribution is symmetric. So in a way, unique uniform captures the fact and gives them equal attribution. It's fair. Also, look at the situation of the Google example, whether you show the ad or you don't show the ad, you complete. Unique uniform will end up giving you 100% because you've got there's a unique path on the way. But if you do the counterfactual adjusted unique uniform, meaning that you subtract out the counterfactual value, then it'll turn out that this particular node did not get any contribution. It did not make any contribution. The only reason that you completed was because you came in with some notions that you wanted to complete in the first place. So the counterfactual aware value ends up solving both of these problems. Going back to the big example, these were all the things that we had before. If you do Shapley value, you get basically uniform, which is 1/3, 1/3, 1/3. It's budget aware, but it's not counterfactual aware. If you do CASV, then you get counterfactual aware, but you get something which is different. It's not budget balanced, it's budget aware. It doesn't attribute everything, because essentially what it's saying is what's happening in node 3, nobody gets value for it. The no ad at stage 3 gets the remaining 33% or 1/3 because it doesn't contribute anything. So it's budget aware, but not budget equal. So now what I'm going to do is switch gears a little bit and talk about how these ideas translate in practice to the data set coming from a large company. So we have a real world data set with millions of paths. There's a single product that this company was trying to sell. And so adoption here or conversion here meant whether you downloaded that particular version, a full version of the software. And in the data set, there were about 100,000 conversions. We had user level data. So each data actually starts off with a sign up. So you sign up on the website of this particular company. And during the sign up process, you have to give your email address. And as a result, I can start sending you email. This campaign went for about 8 months and the touch points were tracked for about 8 months. And during that period, conversion and purchase was also observed. So here were the actions that you could look at. You could send an email. You can observe whether the user opened the email. You could see whether the user actually clicked on an ad or something in the email. You could show them generically. Here, Facebook has been shown generically. There was a collection of different websites on which you can show them a display ad, and you could also measure where you could click. The last one is a little bit strange because what happens with search ads is that you do not get data on when the search ad was shown. You get a data only when the search ad was clicked. So that's why this one does not have the show option, but just the click option. The quit state was not explicitly available in the data. So we basically made an assumption that a customer has quit if there is a certain time tau, after which we don't observe the customer. And at tau plus 30 days is what we described as the quit time. And why 30? Because the scale of the data that we'll see, and this will come up again, was approximately a week. An email was sent every week, and that's what set the time scale of the problem. What happens is that some users in this system neither quit nor convert in the 8 months, and those are people that we could not deal with. And what we wanted to do was compare various attribution schemes and what happens. So before we get there, let me describe a little bit more of the data. Here are the actions, no ad. And here we assume that there was no ad if there was no activity for 10 days. You could send them an email, you could show them an ad, or you could observe a paid search click. We assumed that the users could be modeled using this conversion funnel: unaware, aware, interested, and desired. And as I said at the beginning of the talk, we focused on states that could be completely observable. And we translated aware, unaware to mean no ad received, aware to mean ad received, interested to mean email open, and desired to mean ad clicked. So this is just our interpretation of this conversion funnel. There could be other names for these states. That's not important. The important thing is that we limited ourselves to states that are observable. So here's what happened. When we looked at the customers, remember the customer starts off after signing for an email, signing on this website and giving the email. So they start off unaware. And if you look at what's happening over here, about 50% of the customers did not receive any ad. So this company did not interact with about 50% of the people who signed up. Maybe there was some A/B testing going on in the background that we were not aware of. Of these 50% of the people, about 75% of the remaining people got an email ad. And these unaware people, many of them directly went to search and may also went to click display ads, which means that there were some people of these group of people who came in already well knowing this brand. They signed up and they were well on the way of conversion. So if you think about that for a moment, these are the people that I was talking about, that there is a counterfactual value without having doing anything on these people. They came in already interested, and therefore some of this email effort should actually not be getting any value, and the counterfactual value should be reasonably high.
In the aware state, this was the frequency in which the different actions were taken. In the interested state, that's the frequency. And in the desired state, that was. So as you're going downstream here, the proportion of paid search, which is the black part, is increasing. So there's some initial sort of settling in, but after that, things happen monotonically. About 12% of the people convert from the unaware state, and then it monotonically increases. And remember, a large part of this 12% are actually people who would have converted without any ad action. So this will contribute towards the counterfactual value. We should not have done anything to some of the customers. Okay. Of this, email has the highest frequency, and this will become clear in a moment why this frequency matters. One-step conversion probability is highest for the paid search. So last touch, which looks at one-step conversion, will pay a lot to the paid search. So results aggregated over the various states. What happens here, last touch attribution gives a lot to paid search because that happens to be the completion state very often. Some to display, some to email, no ad. So when people search, they're inclining to buy, does not. So effectively speaking, what's going to happen? Okay, I will get to this question in later. Let me get rid of this. Yeah. Oops, sorry. Yeah. So when people search, they're inclined to buy. And last touch is basically giving all of the value to Google. But in some ways, by the time the search ad is clicked, the customer has already decided that they want to buy the item. And so it's not clear that that search ad is worthwhile. And it's something that one has to worry about. And we will see what happens in counterfactual adjusted Shapley value, whether that can be answered in some way. The uniform ends up giving the most to email. And the reason it gives up a lot to email is because email is sent a lot. And in uniform, every time an action is encountered, it gets a value. And if it's encountered very often, then it just garners up value, whether it's valuable or not. What happens to IVH? So IVH has an issue. Remember in the beginning of this, or somewhere along the line where I defined IVH, I told them as a difference between two Markov chains. But in reality, that's not how it's computed. In reality, it's computed in a slightly different manner, and the frequency with which an action is used ends up increasing the value that that particular action ends up getting. So the implicit idea is that if you're using the action very frequently, it must be because it was valuable. But it's not necessarily true in a counterfactual manner, and that accounts for why IVH gives so much high value. So what does CASV do? So the CASV first ends up looking at the no ad action and says, no ad has a lot of value. And the reason it's basically saying is whatever campaigns that this company was running outside of the digital domain is giving you a lot of traffic. So 50% of the conversion is actually attributable to things that you're doing outside, not in the digital domain. The contribution of email comes down tremendously. The contribution of paid search click, which was 37% here, ends up becoming much lower because the counterfactual value is important. So it accounts for both the counterfactual value and the state of the user. One thing that's there implicitly behind this is both IVH and uniform are stateless, whereas the counterfactual value ends up keeping the track of the state of the customers as well. Let me skip this. Ultimately, what ends up, what the value here is that if you have, whether or not you attribute to states or just to states and actions, ends up making a huge difference to what happens in the system. And it's something that I can return back to if we have time. But in the middle, what I want to do is just stop here and give you the summary of the findings and give an opportunity to have some questions. And if there is some time, I'll go back to some other story. So what are the few things that I want you to take away from it? First, attribution is a central problem in advertising. We have developed a framework to solve this problem. It's certainly not the framework to solve this problem. It is axiomatic, and as a result, it allows you the possibility of either agreeing or disagreeing with what happens with the system. And this CASV, if you introduce a Markovian model, can be computed very efficiently. And using this Markovian model and data, we can extract some interesting operational insights. What is missing? A lot. How do you expand this to a broader set of counterfactuals? We can get into a discussion of that, and it's a serious issue of how do you define counterfactuals. We have to worry about how to deal with dimensionality of the state space. And then another big area that Raghav has been working more deeply on is attribution in other contexts. Ads is just one thing. In many situations, what happens is a number of different actions cooperatively give you the final result. And what you want is a way to attribute value to each of these actions. This is coming up in deep learning a lot. This is coming up in large-scale distributed optimization. And we're trying to figure out how the ideas that we computed over here can be extended to those settings. So I'll stop here and take questions.
Great, wonderful. Thank you very much for this really, really interesting talk. Professor Iyengar, there is one question already in the Q&A that you mentioned from I think a student, Giorgio Costa. You want to take that one?
So it seems that we assume a fixed length of markup chain a priori, 3 nodes. The bidding for online ad means the marketing company pays for ad ahead of time. So first of all, no, we are not. The fixed length that I was trying to show you is just an illustrative example. In the markup chain setting, you could go through multiple chains. So just to get you back, the picture that I wanted to keep in mind is, where did it go? Right here, some jumble of Markov chain. It's a Markov chain. Only thing that we know is eventually something converts or quits. Can we determine the value add for each action if the length is not determined? Yes, that's exactly the point. So the length is not determined, but what we know is what is the value of conversion. And if you look at Markov chain theory, you can compute what is the probability of conversion from each state. There's a deeper question that you can ask is not so much the length that is worrisome here. The worrisome is definition of the state. And how do I, such as sending, so all of these questions that you're asking about repeated emails and so on can be handled. The real difficulty in defining this Markov chain is what is the state space that you'll be using? And how do you then estimate the various transition probabilities? So in the paper, we show that in typical application in the ad setting, the number of consumer paths that we have is so large that estimating the probability distribution is a trivial exercise. The noise there is very small. But then what that effectively means is that we can have a very granular state. And that tension between granular state and the number of measurement paths is an interesting problem that we really don't know how to deal with. So currently we sort of punt that issue by saying we'll get a domain expert that's going to tell me what states are interesting. So that's where we are with that. Any other questions?
Maybe I can ask a question in case others are formulating theirs still. So this incremental value heuristic, it seems like it is close to this counterfactual adjusted if you just normalize the attributions that come out of that. Does I mean, that's a very naive approach, I suppose, and there must be examples where that doesn't work. Can you give some intuition?
In the paper, we actually show, in fact, one of the referees actually just came up with that idea, that why don't we just normalize it, and then everything will work out. So it turns out that you can create examples where the normalization ends up not being the right thing to do. So chronologically speaking, incremental value heuristic was the first step towards getting something which is counterfactual adjusted. In a way, what our inspiration was that can we put it into two things? Can we put it into an axiomatic framework? And then can we say, what is the metric that we'll be using? What is the right metric whose difference makes the right answer? So here what's happening is that the difference, as it says here, it's a difference, incremental value heuristic is approximately the difference in conversion. But when you look at attribution, what you really want to do is look at unique uniform differences in paths. So that uniqueness of the uniform and the difference both matter. Incremental value heuristic gets the first part right, the difference, but it doesn't recognize that it's the uniqueness of the state that matters, at least in the Markov chain setting. If you keep coming back to the state, you shouldn't get more and more and more attribution just because you came back to it. And correcting for that gives you counterfactual adjusted Shapley value.
Okay, great, thank you.
Let me just quickly see if there's anything in the chat box. Okay. All right. So there was an option of somebody was asking that they wanted the slides. I'm happy to share the slides. I guess I can just email it to Laura or you, and whoever's interested, we can put it.
Yeah, if you want to send it to me, I'll make sure it gets to the participants.
Okay.
Okay. Well, if there are no additional, oh wait,
there was some...
there's one additional question about connections to inverse RL.
Absolutely, deep connections to inverse reinforcement learning. Yes, so that's a very perceptive question. Yes, there is connections, and with a different student, we kind of made we have a KDD paper where we try to connect this to inverse reinforcement learning. The right thing would be some sort of an inverse causal reinforcement learning, and I don't quite know how to do that. The right concept that would be needed would be that, or inverse counterfactual reinforcement learning. There's a colleague of mine, we just joined Columbia, Elias Barenboim, who's been looking at causality in Markov chains. I'm hoping that in collaboration with him, we'd be able to answer some questions, but we don't have an answer.
Okay, well, maybe with this, we'll close the seminar. Thank you everyone for attending. And again, thank you, Professor Iyengar, for joining us today.
Thank you very much.
Wonderful
Thank
talk.
you for inviting me. I hope people enjoyed the talk.
Absolutely. And I think that's it. Laura, I guess I'll leave it to you to close the recording and manage the rest of the webinar.